So, welcome back. So our next presentation is coming from Jena, from TTTech. TTTech is also a long-term contributor to the Ethernet ecosystem. TTTech is very, very active at IEEE 82.1 in the TSN working group. And they have really deep analysis and bring very good contributions to the community. Our first speaker is Jakob Zwirchmayr. Jakob is working as a software architect in autonomous driving products and pre-series group, where he continues developing platform concepts and analyzing new technologies for other systems. He received his PhD in computer science from Jena University. After joining TTTech, Jakob worked on a static program analysis tool for formally review generated. Autos are compliant. Oh my God. Soon he joined then the ADAS team at TTTech, where he worked in pre-series and advanced engineering projects. Shashank Gaur is our second speaker. He's currently manager of pre-sales in the system engineering department at TTTech. He and his team is responsible to understand customer needs and finding solutions and enrich the TTTech product portfolio. In his past roles, he also contributed for communication system and scheduling in various domains, including also in automotive. So welcome on the stage. Thank you. The floor is yours.
Thank you. Good morning, everyone. So I think I should rephrase the title to the follow-up to the previous presentation. So thank you, Anil, for setting up the stage very well for us. We are going to talk about similar topics, especially the recent work we have done to deep kind of look into how this service-oriented architecture vision can really work in some real application scenarios. And to talk about real application, I wanted to start with a basic vision or basic view we have of typical single ECU functions. And this is something which exists today, which has existed for a while. You have a single ECU function which has certain sensor inputs, certain pre-processing, then computation, and then control. And usually this exists, or till now it has existed on let's say, function-specific ECUs or commercial ECUs which do that job, but also sometimes come with control loops which have strict timing requirements. So specifically in ADAS domain, you would see these single ECU functions having requirements. An example is the vehicle needs to stop and within certain time at certain speed because an event happens. So there's a strict requirement to the parts of the function which needs to happen and provide input to the second part of function, and this is very well known as an event chain. This now evolves from single ECU to multi-ECU ecosystem as soon as we start talking about zonal architectures and software-defined vehicles. So we saw in the keynote as well and Anil's presentation earlier today morning that this is something which is real and is happening and needs to happen if we want to go for the future of software-defined vehicle. And this we already see in terms of the evolution of the whole vehicle architecture. So on the bottom, the commercial off-the-shelf, either sensors, actuators, they will remain for a while and maybe for a long term. But the key aspect is there are zonal ECUs popping up, which are able to act as a gateway, as a business function, and really variety of let's say variants here, serving the central computes, which in the end are really making the decisions. And those single ECU functions now have to transition to this zonal architecture, which has this whole up integration of the applications. And this requires a much higher integration of applications towards the hardware. So no more isolation of applications on a single ECU, which means that you have to share resources, which means you need to make sure that you are able to execute on an SOC, which is also having other functions coexisting or co-located. So this is a really a tight need for those applications which have these strict timing requirements. And we definitely see that this needs to be covered and satisfied for the vision of the zonal architecture. And to achieve that, a consolidation of, let's say, hardware, but also communication paths needs to be happening so that we can provide these timing guarantees and achieve the goals of these functions, which now needs to transition. And also, of course, to really achieve the software-defined vehicle vision, we need to provide an update to those software over time. So not just one time, but as Anil talked about, I think, quite extensively, that upgradability or updatability is a must. But this doesn't happen just bottom to top, just to focus. So zonal architectures are not just coming out of the box. They are evolving. OEMs are working with multiple brands inside them, and they have different vision of zonal architectures as well. So this is not just a bottom-up integration, but also kind of a distributed integration, which means that kind of functionalities needs to realize in software in a way that they can coexist, they can be located. I think Anil also talked about location transparency that needs to be brought in. And as I said, resources needs to be shared. So there are different vision of the zonal and central computes, and to really achieve that, the whole network needs to come together and satisfy the guarantees. And of course, more and more the cloud and edge topics become more relevant also. So not just in the car, but supporting those application locations in outside the car and serving components which become part of this event chain, which I showed you. Which means those event chains are not going anywhere, right? They still exist. Those functionalities still need to happen. The difference is those need to be realized for different architectures, especially in software-defined vehicle ecosystem. They need to be able to be developed, kind of abstracted from the hardware and deployed on different variant of the architectures. So the same OEM might want to use the software on one architecture and on another brand in another architecture. So this is really needed while satisfying the timing, let's say, requirements which this whole functionality, or what we call event chain, has, which brings some consequences. What are these consequences? So as I talked about, in the world of the legacy world, the single ECU functions, they were coming from same ecosystem. So if you were doing a control application, you could do it in classic AutoSAR world, but now you are sharing the ecosystem as well. So an event chain could be composed of classic AutoSAR, POSIX, different kind of application, and those needs to be integrated on these SOCs. While maintaining these real-time guarantees, providing them the freedom from interference so that they can execute, they can be reliable, they can be safe, and that's a very essential part of the zonal architecture, and must be satisfied for certain ADAS and AD applications at least, but also we see in other domains that is also needed, and this needs to be done on a distributed and heterogeneous hardware, so not just for one SoC or one type of ECUs, really covering a range of environments which have mixed criticality, so not just ASIL-D applications, also a mixed bag of applications and requirement. So to achieve this, everyone is going for software. I think we've heard this quite enough, that software is the future, software-centric future is there. But to really achieve that future, you need a good tooling, and that would be the focus of solution, we think, for the future. So you really need to enable the software developers and system integrators to have a robust tooling which can achieve these, let's say, zonal architecture deployments. But you also need to kind of manage the complexities in the software applications and provide the developers the ability to update their software without thinking about the location where the application will be deployed. So that's what is called location transparency. And of course, the signal-oriented world, or the signal world, is not going anywhere immediately, so we need to manage that as well. So there are a lot of consequences of the zonal architecture which we just saw. And if I was a pessimistic OEM system architect, I would say with SOA, I'm getting kind of worse of both worlds. I'm still keeping this signal world. I have to convert signal to SOA. I have to compromise performance there. And also I have to kind of do a whole another development cycle in parallel to achieve this new software-defined vehicle. But we are not pessimists, we are optimistic. And I think Jakob will now take over and talk about our solution to some of these problems.
All right, thank you, Shashank. So as Shashank mentioned, and to give a very short recap, so basically we are in a situation where we can assume very little about the hardware environment that we want to deploy our software on. And at the same time, we are in a scenario where we want to deploy updates to our software rapidly and more or less constantly, so the whole DevOps cycle. What makes it really hard is this safety aspect that we discussed before also. So we are not in a situation where we can just push updates and maybe they work, maybe they don't, because we're in a safety critical system. Even more so, we are getting into a situation where more and more, because of the sharing of resources, we actually look at a mixed criticality system. So we want to deploy the safety functions and in a way the comfort functions at the same time. And the whole software development process needs to be basically speed up so that we can fulfill this. And basically that with SOA we get the worst of both worlds. It's coming from our customers in a sense, because in a way we didn't manage, even though we have service-oriented architectures. I think that in automotive what we so far didn't manage is the location transparency that Shashank mentioned. So in a way in the rest of the talk, we are going through a technology stack that we are currently exploring and working with and getting to serious quality, where we can really deliver this location transparency while at the same time adapting our software development workflows to modern workflows where we can actually push updates very rapidly. So what is the technology stack that we are looking at? And just as a comment, it's definitely not the only one. What we want to describe is what are some of the key aspects that such a stack needs to fulfill. Working in product innovation, what I've seen multiple times is that we have new approaches, new ideas, cool new features. We prototype them, we develop them, and they never get into serious. Why don't they get into serious? Because usually we have a switch of the technology stack from something that we use for prototyping to something that we can deploy in serious. So basically, what I'm saying is that what we have to do is we have to end, in a sense, the split between the prototyping, the constant development, and what we actually deploy in serious. This stack needs to be the same stack. Now, I'm mentioning ROS here. It's a nice framework for prototyping. You get results extremely fast, but you can, of course, not deploy it in serious quality. But what is one of the key aspects? One of the key aspects is that below the whole ROS framework, you have a middleware technology that is called DDS, Data Distribution Service. And it's a middleware for distributed real-time systems. It's a communication stack, and this communication stack you can actually get into serious quality. So what do you end with? Essentially what you get is an environment where you can do prototyping, you can develop your data model, you can develop your system, your functions, and once you are confident that your function actually works, you transition it to serious quality by just stripping those parts that you cannot get into a car, so basically those ROS frameworks. But you keep the data model. So whatever, for example, basically data in DDS called topics is basically the main thing. You do not care who produces data. You only care about the data that you're interested in. That goes as far as you are never, in DDS, you are never telling who you want to communicate with. You're only telling what are you interested in what information are you interested in? So for example, actually, you are defining more or less queries where you formulate the interest in data. So you might say, I'm interested in a certain sensor value. I don't care where it's coming from. I need a specific sensor value. And that already goes into the direction of this location transparency. What is another aspect that we should fulfill? So we were talking about the safety critical aspect and, for example, timing guarantees that relate to the safety critical aspects. What DDS allows you to do is specify for your applications, in your application, requirements towards the environment and other application, so-called quality of service parameters. So you might specify, how often do I produce data? What is the maximum data age that I'm interested in if I consume data? And that is important because suddenly by specifying those, let's say, application desires, you can already specify them during prototyping in your applications. So while you develop your prototype system, you already also develop kind of the requirements that you expect from your environment, the timing properties, for example, execution properties. And there is other benefits of DDS and the technologies we are aiming for. For example, it would also, with this thing that we call SENO here, it's a low-level protocol, and one of the benefits is we can actually also communicate over wide area networks, not just in local networks. So in a way, the nice thing is you have a prototyping framework API, and you have the same API when you develop basically the serious version of your software. And if you move a function to the cloud, as we heard before, by relying on this low-level protocol, you don't need to switch technology. It's one stack, no matter what you do. And the stack, as I said, is location transparent. So now the question is, how do we use this stack? And what's the main idea of the approach? So one of the main ideas is, you develop your software system, you have your nodes, they communicate, you know the data that they exchange, but still you didn't define the system that you run on. So the main idea is, once you have your system specified, and in a next step, in a later step, you basically specify your environment. And by environment, for example, what is meant, you specify what is the actual hardware topology that you deploy on. What is, for certain subsystems, what is the software topology that you want to deploy? Some applications you can only deploy, for example, on an SOC that is rated up to ASIL-D. So there is certain constraints regarding where you can deploy certain applications and functions. And then, of course, you also have certain properties about your software. As I mentioned before already, how often do I produce data? How often do I run? What is my execution time, if it can be characterized? And as Shashank mentioned in the beginning, also you have these event chains where you specify usually an end-to-end latency, and based on that end-to-end latency for the whole chain, you basically compute constraints and requirements for each single node in your chain. Now, why would this help us reach basically an SDB? It's quite simple. You have your system specified, your event chains, and now basically, no matter what the actual hardware is that you want to deploy on, the only thing you have to do is basically add a description of your hardware topology and some aspects about your software. And then the rest can be fully automated. So basically, by fully automated, what I mean is, with these constraints that are specified externally to the software that you developed, you can compute schedule tables, and we are using, for example, TSN QBV for the network layer. We compute schedule tables that basically describe precisely how those applications exchange information. we add the timing, and at the same time, we also compute basically task schedules that are, in a sense, they are very similar to what we do for QBV. In QBV, we describe when do we open gates so that information can flow through. With task schedules, we essentially define when will an application be executed on a certain SOC. And because this is fully automated, what you have is your software system, somebody specifies your hardware topology, and you throw the whole thing at a tool, fully automatic, based on logic and heuristics, and what you get is schedule tables that describe how software executes on your SOCs. You get schedule tables that describe how and when information flows through the network, and at the same time, you get basically configuration files that you can just provide to your applications. When the application starts, they load the config file, and the application will more or less behave like you specified in the configuration. So basically, to recap, you start by doing your function. You get a data model described here as interface definition files, and that's it. You have your function implemented. Now, you make up some constraints. Those constraints will basically decompose to constraints for all of these blocks. And now in a later step, you describe your topology, your hardware topology, and then you run the tool. And to make it, let's say, to go through it stepwise. So basically, again, the function you have either in your applications, you can do it directly or you can add it later. You specify the quality of service that needs to be fulfilled. You specify a certain amount of deployment configuration, and you specify certain things about the execution behavior. And now if you throw it at the scheduling algorithms, what you end up with is basically what you've seen before. We get schedule tables and configuration. It's again, as I mentioned, when do certain applications execute on the SOCs? When are they communicating? And in a way, the solution that the tool gives you, by construction, it is correct. So basically, the requirement, the latency requirement for the event chain, it's reflected in the solution that the tool gives you. So suddenly, even though you might have various hardware topologies where you deploy on, so for example, here we have 2 nodes on the middle ECU, here we have two nodes on maybe the kind of the first ECU, and here we have 3 nodes on another ECU. It doesn't really matter. Once you specify the hardware topology, the tool will basically compute a table, and those tables, they will always fulfill all the requirements that you gave. So in a way, the implementation of your function that you have, it's independent of the actual topology, and to provide safety, you run a tool. So now you are basically in a situation where you can have one technology stack to prototype, you deploy the same technology stack in the car, and you're basically using a tool based on logic that synthesizes all the execution constraints that you need to run your software safely. And to give you an example, so this is a small prototype system where we tried to apply this approach. So basically, we did a bunch of DDS applications. We deployed them on hardware, and then we run them. As soon as we start, and we assume this is a safety-critical event chain. As soon as you start loading the system, for example, in this case, we perturb the network, you suddenly see that the system starts misbehaving. So basically what we do then is we take the constraints, we throw it at our solver, and the solver gives us configuration files, schedule tables. We load them, so we don't even need to recompile the software, we just load them. And now you have the same function running on the same hardware system. We even have the same disturbance on the network. So here actually we are running iPerf twice, so the switch gets overloaded, starts dropping messages. In this scenario, the only thing we did is we load our config files, and as you can see that the system behaves as it should. again, just in a bit more detail. So basically, by loading the config that we compute with solvers, we don't lose any more messages. We don't have packets that get delayed. And the same actually applies also to the task level running on different SOCs. As I said, it's comparable in a way to QBV schedules. Basically, here you see we don't load our schedule tables, and the application is just running freely. As soon as the CPU load goes up, you see the higher it goes up, the more violations of our time bound. This line here we get. And then again, once we load our schedule tables and the applications are actually scheduled according to this configuration, we never violate our execution time bound. And the main idea is this tool that computes this configuration, it can run in a pipeline. So you can run it basically anytime. You don't need any human intervention. And that is what in the end enables you to basically deploy your software safely, no matter what the hardware topology and the hardware configuration is. And with that, I conclude. Thank you very much.
So thank you very much. Are there some questions? Sorry. Jumping. Okay.
So I'm Ricardo. Hello.
Yeah.
I'm Ricardo Robert Bosch. Great presentation. Can you tell a little bit more about how you managed from the DDS to the layer 2 in the same computer? Because this is from real measurements, right?
Yeah.
How you managed to go through the stacks in your software? You did in ROS, right? ROS 2 you said.
So here we actually, we did not use ROS nodes in the beginning, but we just basically developed DDS applications. So in a way, the ROS aspect, it's mainly to develop your data model. So you know which flows do you have through the system. Still not basically deciding from where to where those flows are, but just defining the flows. And in a way, what is necessary is then at some point, if you are deploying a critical application, then you have to specify something about the location actually, because you want to create a TSN schedule. So you need to define where is my talker, where are my listeners. So you have to define topology at some point, but it can be very late. That's in a way the key idea, to decouple deployment from actual software function.
Thank you.
Albrecht?
Yes, thank you. Albrecht Schwarz from ETAS. I'm curious about the protocol stack. I think DDS is an IP-based application protocol, so it's probably DDS over UDP, IP, TSN?
Yes.
Okay.
In general, it's agnostic to the transport, so you can also do it directly over Ethernet.
So is here directly over Ethernet or with IP?
Here we used UDP.
UDP IP?
Yeah.
Okay.
UDP IP.
Thanks.
All right. Any further question? So then, thank you again. It was a very good presentation. Oh, come on. We have time.
We can follow up later on as well.
Okay, this is quite interesting. So this is the first time I actually hear someone actually using QBD for schedule tables.
Yeah.
Because I know there's a big push towards using QCR, and because QBD is too complicated to configure.
It's in a way we always get that, but we don't really believe that it's more complicated than the other standards. I mean, we are scheduling systems with I think the largest are like hundreds of switches, a huge number of links, and actually combined with QAV rate constraints. So I mean, there is network calculus. It's a logic. It's NP complete. You might need heuristics that your solvers get fast, but it's not a problem that is not understood, I would say.
Right.
You can construct huge systems using QBV.
But I think that the tooling and the heuristic algorithm is the key part here, which allows you to reach the successful, let's say, solution. So the solution space is large. That's the main problem, and it takes time to find a solution. But if you have a good tooling and right inputs, which the tooling allows automatically to figure it out, so that's really helpful.
Okay, and just one more. So, okay, so I understand this is for DDS-specific traffic that you would use QBV. Because I guess there's other traffic that's basically, it's event-driven type of traffic where you can't really schedule. And so you got to mix that along with your
Yes.
DDS
Yeah.
traffic. And of course, those events are probably higher priority traffic.
So even so the prototype is very simpler, but overall we imagined in terms of scheduling there needs to be certain kind of flexibility as a rubber band. So to allow, and that's the approach. We take kind of a bigger bound, which we call the computation chain bound, and under that computation bound we allow the tasks and network to kind of flex a little bit. That's our kind of view on that. So there needs to be an overall bound on the whole vision of the function you want to achieve, but you can kind of have an elasticity to allow those kind of behavior exactly. And then you have to develop specific policies or specific aspects. Yeah.
And on task level, when we speak about, let's say, time triggering the applications, actually we have variants of how strict we are. And in a way, you can also use the schedule table to more or less just provide an execution time guarantee to applications. They don't need to use exactly that slot, but if they didn't get CPU time before, basically in the event-driven world, as soon as you have data, you run. But basically, when your system gets overloaded, you will not run. And then at some point, there is your computed time slot where you can run, and then you get the guarantee that you actually get the CPU. So it's kind of like a backup slot where for sure you will run. And that's, again, to basically have worst-case end-to-end timings that we can guarantee.
All right, thank you. If you want to discuss further, there's the speaker's corner after the session where you can dig deeper. Thank you very much.
Thank you.
Thank you.
Thank you.